Hi, welcome to Chemistry Made Easy. Today, we are going to continue with part 2 of radioactivity. In part 1, we defined radioactivity as the process whereby an unstable nuclide will disintegrate into other nuclei with the emission of radiations and energy. So when we talk about radiations, what are the various radiations we can talk of? We said that when we talk about radiations can be either alpha, we have an alpha radiation, we have a beta radiation, and we have a gamma radiation. So either alpha, beta, or gamma. So today we are going to take these three forms of radiations and then we are going to describe them in terms of their nature, their charge, their effect on magnetic and electric fields, their penetrating power, and their ionization or their ionizing power. So let's look at that. So if I have my radiation, let's say an alpha. Now, alpha radiations are also considered to be helium nuclei. So helium. So in terms of nature, we can describe alpha radiations as ionizing helium nuclide. The next is a beta radiations. Beta is also considered as electrons, so they are similar to electrons. So we can also talk about beta radiations as high speed electrons. And the last, another list, is gamma. They are also similar to X-rays. So gamma radiations are also described as electromagnetic waves. So we can consider them as electromagnetic waves. Okay, now let's look at the charge. For their charges, we said that normally the charge of a nuclide is the same as the atomic number of the nuclide. So when we look at alpha particles, you can see that they have an atomic number of 2. So these alpha particles, in terms of charge, they have a charge of +2. Beta has a charge of -1. Gamma has a charge of 0. Now let's look at the effect they have on electric fields. Now, because these nuclei or alpha particles are positively charged, we normally say that they are deflected towards the negative plate because a positive plate cannot go towards a positive plate. They will repel. So the deflection is mostly towards the what? The negative plate. So there is a deflection when we come to so they are mostly deflected and they are deflected towards the negative plate. So the beta particles are also high-speed electrons. So normally we say that because of that, because they have a negative charge, they will be deflected towards the positive plate. So There is also a deflection here, and it's towards the positive plate. Now for gamma, because they have no charges, there is no deflection. Okay, so you can say no deflection, or you can say not deflected. Now let's look at the magnetic fields. So effect on magnetic field. For the effect on magnetic fields also have what? They are charge fields. So basically, there is also a deflection here, and there is a deflection here, and there is no, or it is not deflected. Then let's look at the penetration power. So for penetration power, we say that alpha particles normally have low penetration, whilst beta particles have moderate penetration. Then for gamma particles, they have a very high penetration. Then when we go to their ionizing power, for ionizing power, alpha particles are the one with the most ionizing power. They have high ionizing power or ionization power. Then for beta particles, they are moderate. Then gamma have low ionizing power. So this is the various radiations being described in terms of their nature, their charge, their effect on electric fields, effect on magnetic fields, their penetration power, and their ionizing power. Now the last thing we'll be looking at is the stability of a nuclide. Stability of a nuclide. We say that nuclide stability can be based on the following. One, we have what we call the neutron-proton ratio. Also, it can be based on binding energy per nucleon. And the half-life of the nuclide. So these three factors can cause the stability of a nuclide. Now let's explain the first one, the neutron-proton ratio. We said that when you take an atomic nuclide, and then that particular atomic nuclide have a neutron-proton ratio of 1.0 or 1:1, we say that that particular nuclide is considered to be stable. So for instance, if I have, let's say, carbon, it has a neutron 6, we subtract 6 from the 12, we get a neutrons of 6. We divide it by the proton 6, we're going to get 1/1 or 1.0. Because carbon has a neutron-proton ratio of 1:1 or 1.0, we said this particular nuclide is stable. But if I take uranium, which has 92 and 92 and 238. If I have 238, 92, so we have 6, we have 4, so I have a neutron of 146 divided by 92. you realize that I will have a neutron-proton ratio greater than 1.5. So because of that, uranium cannot be considered to be what? Stable. Okay. The next one is the binding energy per nucleon. Binding energy per nucleon. So binding energy per nucleon. When we talk about nucleons, it is the number of protons and neutrons in the nucleus of the atom. So it's basically like the mass number, okay? Because the mass number is gotten from the protons and the sum of protons and neutrons will give you your mass number. So in the nucleus, the protons and neutrons give us what we call the nucleon. Now, we are saying that in the nucleus, if you have a greater binding energy, then that means that that particular nuclide is also considered to be stable. Okay, so if I have, let's say, uranium 92 and 238 and carbon 14, these are two unstable nuclei. But if you want to look at their stability based on the new binding energy per nucleon, then we are saying that uranium 238 will be considered to be more stable than carbon 14, because in the nucleus of this atom, in the nucleus of this new radioactive nuclei, uranium would have more uranium will have more protons and neutrons in its nucleus than carbon 14. Therefore, we say that uranium will be more stable than carbon 14 based on the binding energy per nucleon. Okay, so then the last one is the half-life of the nuclide. So the half-life of the nuclide. We say that for the half-life of the nuclide, if you have a nuclide that have a longer half-life, then that particular nuclide is also considered to be stable than a nuclide that have a shorter half-life. Because those with shorter half-life would undergo what? A very fast disintegration. They will break down easily. Therefore, we cannot say that they are what? They are stable. But those with a longer half-life, they will have what? Their disintegration will take a longer time. Therefore, they are considered to be more stable than nuclei that have shorter half-life. So the half-life of a nuclei can also determine the stability of that particular nuclei. So that brings us to the end of part 2 of radioactivity. If you enjoyed this lesson, I urge you to subscribe to Chemistry Made Easy and like, comment, and share.